All right. All right, so why do we need to be able to do this? Because today, what our overall goal today is to get some more derivative rules like the power rule, right? Where we can find f prime in a shortcut way, right? And not do the whole limit definition kind of thing. So we want to find some more shortcut rules like the derivative of sine is cosine, right? We want to add, and we're going to make a list of those. And then what we'll do is we'll apply that to the chart kind of questions. Where's there a local max, local min, that kind of stuff. We're also going to add in the inflection points in concavity, which means what? Where do you find inflection points? Where do you find concavity? What derivative?
Zero.
Well, okay.
Local maxes and mins.
At local max and mins of f prime. Well, how do you find local max and mins of f prime? Where f double prime is 0. Remember when we were learning about f double prime, I said when you hear f double prime, you should think concavity, because you look at the chart in the f double prime row, basically what it tells you is concavity. If f double prime is positive, f's concave up. F double prime is negative, f's concave down. F double prime is 0, that's a possible inflection point. So we get into questions about concavity and inflection points. Now we need the second derivative. But that's just the derivative of the derivative, right? So if we know these derivative rules, we can do it. So there's going to be a bigger emphasis on those kind of problems. Okay, so that's a big part of what we're going to do. But then what we want to do is set those equal to 0. So local max min, we do f prime, set it equal to 0, solve. Find inflection point, we do f double prime, set it equal to 0, and solve. We're going to be solving a lot of equations. On our calculator, it's pretty easy because we can tell it to just solve. I didn't say this yesterday. This was supposed to be a no calculator worksheet. You really should have been able to do every single problem on it, except number 21, without a calculator. You should have been able to do every single problem without a calculator. Because if you're going to use a calculator at all, since we got these really nice calculators, you just go in and type in solve, put it in, comma, whatever the variable is, and it just solves, right? So that part will be easy. Now, there'll be a few things we have to learn about the calculators when we do that to solve those things. But otherwise, it's pretty easy, pretty straightforward. So it's the no calculator part of solving we have to be able to do. So let's take a little bit of time here to work a few, and I would guess we would probably focus more on the back page, although I'll make a couple of comments on the front page. Most of the equations we have to solve are going to be set equal to 0, right? But I want to make a comment on 5. If you had to solve something like this, what would you do? Wouldn't you FOIL that out? And then what? Move the x over, get 0 on one side, right? And then look at factoring it and whatever the case may be. Okay, so make that comment on that. This one, we could FOIL all of these out, but actually I wrote it this way for a reason. What else could we do right here? Yeah, each of those terms has an x minus 2 squared in it. So we can factor out an x minus 2 squared. I don't have to use square brackets there, but I always think it separates it a little bit. But if I take out an x minus 2 squared, what am I left with there? X minus 2 to the first minus 1, which would be x minus 3. And so then so basically I have that. So this turns into x minus 2 squared times x minus 3 equals 0, and we get that kind of thing. Okay? So that is kind of those are some tricks or some things we'll see from time to time. I think one of these didn't factor this one. Yeah. So how would you solve something like that? The quadratic formula. The quadratic formula. I'm not saying there's going to be very many times where you're going to actually use the quadratic formula, but it does come up. It does come up in some problems. So solving a quadratic where it will not factor, we would plug those into the quadratic formula, which is negative b plus or minus square root of b squared minus 4ac all over 2a, right?
But what if you get a negative?
If you get a negative under the square root, what's that mean? That means it's no solution. So, and I like what Matt said because he's talking about graphically, and I like to think of it graphically as well. We're asking, where does that graph equal 0? Well, we know that's a parabola. Well, a parabola could do that, right? Does it ever equal 0? No. Well, that's the situation, or that is the situation where, in this case, we know it faces up, so it's got to be that. We know that there's no solution. The parabola could come down and just touch. That's when you get a perfect square in here. No, I'm sorry, that's when you get 0 in here. Because then you get negative b plus or minus 0 over 2a, which is just one solution, negative b over 2a. And then, of course, your parabola could go down and do that, and you might get 2 solutions. And that's the plus or minus. Okay? That comes into play, actually. I'm glad you said that, because one of the problems I know we'll touch on later on, it always comes up in the practice tests for our midterm exam, where they give you a quadratic kind of thing. And remember that one we did with the cubics, where what are the situations where you could have 1 root or 2 roots, right? Remember that one? Well, I've seen that a lot with parabolas. Well, what determines whether you have 1 root, 2 roots, or no roots? It's that right there. That's called the discriminant. Okay, and it's the b squared minus 4ac that determines. If it's negative, you've got none. If it's 0, you've got 1. If it's positive, you'll have 2. Okay, so that's something that comes up later on in some problems. Okay, when you get into these problems, I would cross multiply. It's not a bow tie because you're not getting common denominators. You're not adding 2 fractions. You've got 2 fractions equal to each other. Now here you could do a bow tie. Okay, here you could bow tie on this side. Now the other thing you could do on a problem like this is, and I know Mrs. Andreessen talks about this, is you could just clear out your fraction on both these problems. I could just take this side times 6x and this side times 6x. You see how that would clear out that fraction? Because on this side, that would give me 2x on top. And on this side, this would give me what? 3. And then I could solve from there. Okay? Now you got to be careful on that because whenever you multiply by an x, you lose solutions possibly, like 0, or you gain extraneous solutions. So you got to think about those kind of things. Doesn't, again, come up a whole lot, but sometimes it does. X couldn't be a 0 in this problem anyway because of this original problem. There's an x on the bottom, and that would have been undefined. So x can't be 0 anyway. On this one, you could just multiply both sides by 2x, right? On this side, you would distribute, you would take both of those, and again, that would clear the fractions out. So that's a technique you could do as well. Or you could bow tie it and get solutions there. Okay, this was kind of an interesting one. Write a quadratic equation that has added solutions. Anybody got an idea what you do there? Yeah, just write it as factored, right? X minus 3 and x plus 1/2. And then FOIL it out and maybe get the fraction out of there or whatever. And, you could multiply both sides by something. That would be an equation that would have 3 and negative 1/2 as solution. Okay, so just a different way, because you know what this is like, and we'll see more of that as we study for the midterm, these different ways of asking these kind of questions. Okay, I really want to focus on exponential, log, and trig today, which is on the back. So I'm going to make a couple of points here. So like on 13, I would say we write this in exponential form. So 2 raised to the 3rd equals x plus 5. Then that's pretty easy to do there. This is one that we had done in the beginning of the year on Appendix E, I believe. So we go and solve a problem like this. We would do what first? Divide by 20. Now, there's a couple ways we could go from this point. But the one I like to do you remember the one I talked about doing? Natural log of both sides. Do the natural log no matter what the problem is, no matter what the base is. I would say do the natural log of both sides. Now, today in our homework, there'll be a little bit of this. We'll be getting into some these exponential functions and solve. I'll show you a little bit on the calculator today as well. But bring this down in front, so you get 0.1x times ln. What's ln? ln is 1. Those are 2 we got to know. ln is 1, and ln1 is 0. Those are two natural log things we need to know. Okay? So anyway, ln e is just 1, and here we got ln 4. Now we would divide by 0.1. Now 0.1 is 1/10. If you divide by 1/10, you're multiplying by 10, right? So really we get x equals 10 ln 4, and that's how I would like you to leave your answer. Now, if you did this one on your calculator, if you typed this original problem in your calculator and told it to solve, number one, it would give you a decimal answer because of the 0.1. Okay? But if you put 1/10 there instead of 1.1, then it would give you an exact answer, but it wouldn't give you 10 ln 4, it would give you 20 ln 2. Why? 2 squared, and ln of 2 squared, we can bring the 2 down in front, and ln 4 is the same as 2 ln 2. I don't care. I will accept 10 ln 4, that's fine. Just understand when you go to your calculator, it might write 20 ln 2. You didn't do anything wrong. It just wrote it in a different form. So this process right here, I think is pretty important because we will have some no calculator problems with exponential functions that you will have to solve, and they'll look like that one right there. Okay, so of all the exponential ones on here, that's probably the most important one to be able to do. Okay? All right. Now, when you get to one like this over here, now you've got, again, an exponential. You got x up here. I would do the log of both sides. Okay, even though there's a 5 there, I would do natural log every single time because that allows us to do what? Move the power down. So the x minus 1 needs to be in parentheses. Now we run into all kinds of little algebra tricks we got to be careful of. This side is just what? 2x. Okay, now let me talk about this because this is an algebra thing that's going to come up from time to time. It's something we'll be seeing in various forms today. So at this point, we want to get the x by itself. Okay, now what's ln 5? A number. I don't know what it is. We get our calculator tell, but it's just a number. It's like a 7, whatever. That's not what it is, but it's a number. Okay, what would you do right now if you had x minus 1 in parentheses and then a 7 outside? You would distribute, wouldn't you? So that's what we should do here, right? We should distribute, but it doesn't feel right because we're not used to seeing an ln 5 out there. But ln 5 is just a number, okay? So we should distribute that. Now, when we distribute that, we write it a little differently than we often would. Normally, if I take a 7 times x, I would write it 7x. Well, I don't want you to write ln 5x because some of you are not in the habit yet of putting parentheses, and so some of you would write ln 5x like that. Now, to me, that's confusing, isn't it? Is that ln of 5x or is it ln 5 times x? Now, if you do a good job of using parentheses, then you shouldn't have an issue, right? It would be that. But most of the time, what you notice when you have a problem like that is when we do ln 5 times x, we actually put the x in front just to avoid that confusion. Okay, but this is nothing more than like 7x. This is nothing more than a number times x. Okay, so I distributed there, and then I take that times 1. So that's minus ln 5, and then over here I got 2x. Okay, now, again, let's pretend that ln 5 was a 7. So if you had 7x minus 7 equals 2x, what would you do? You'd get all the x's, well, you might, but you'd probably move the x's all to one side, right? And get the non-x's over to the other side, right? And that's what you want to do here. So we don't often think about these simple algebra things that we've done way back in 8th grade because we're used to doing them with plain numbers, not numbers like ln 5 or pi or things like that. And we'll see these from time to time. So what I would want to do is get the x's all to one side. So x ln 5 minus 2x, and then add this plain number over to the other side. Does that make sense? Now what do I do on the left side? Factor out an x. I always like talking about this because we never did this when we learned it. When you learn, I always want to do this with my classes when I used to teach like 8th grade, or I used to teach Algebra 1A where you're learning equation solving. And, you know, so you learn that 2x plus 3x is what? 5x. And you just learn that. And the problem I always have teaching this is, once they learn about multiplying and adding powers, then all of a sudden they want to do 2x plus 3x and they want to get 5x squared, right? I have the hardest time explaining why that's not 5x squared, right? Because they learned that multiplying, you add the power, so why not adding, right? And the problem is when we're learning that, we haven't done distributive property, we've done distributive property, but we haven't done factoring yet. So they don't know about factoring. When you do 2x plus 3x, what you're really doing is you're doing this, right? You're factoring out an x. And you get 2 plus 3 is 5. Okay, but you don't think of it that way. You just do, you guys know 2x plus 3x is 5x. Okay, and I always wish I could show them that, but they don't know about factoring yet when they're learning that. Okay, so anyway, we take out an x. We get ln 5 minus 2 equals ln 5, and then we divide by that quantity. So this little process is actually going to come in handy in something we're going to learn later this year as well. But that's your final answer to number 15. No calculator necessary, right? No calculator necessary to solve that problem. You just leave it in terms of that. Okay? All right. So, moving on down, let's get into some trig. Oh, this one's interesting. 16. This is actually a FOIL problem. E to the 2x can be written e to the x times e to the x, because when you take e to the x times e to the x, what do you do with the powers? You add them. So e to the x times e to the x is e to the 2x. Now, I'm not sure this is ever going to come up, but it's a good review of some algebra things. All right, and then to make a 2, you have a 1 and a 2. 1 and a 2. You subtract 2 e to the x minus 1 e to the x is minus 3 e to the x. And so we get e to the x equals 1, or e to the x equals 2, right? And then do the log of both sides. Of course, this one is easy. This one's just x equals 0, right? E to the 0 is 1, so x equals 0. And log of both sides, well, or just put it in x, it's just ln 2, right? ln 2. So 0 and ln 2. Do the log of both sides. Jared, you have a question?
I had a question on the last one.
Okay.
Because your final answer was ln 5 over ln 5 minus 2.
Yeah.
You can't cancel this at all.
Ah.
Just
Oops. ln 5 over ln 5 minus 2. The mad canceler. There it is. He's just wondering. It's a great question. I'll tell you what. Let's test it out. Let's do 7 over 7 minus 2. Would that be the same thing? So that's 7/5. Yeah, if you put, yeah. Good work, right? When you see an addition sign, here's the thing about cancel. We had a teacher here a number of years ago, taught honors algebra 2 before Mrs. Andreessen, and she forbid the use of the word cancel in her room. She hated the word cancel. Now, I never got quite so caught up in it. As long as you remember that what you cancel are factors. You cancel factors, right? That reduce to 1. So they have to be factors. So my question is, can I cancel the ln 5s? What I would say to you is ln 5 a factor of the top and the bottom? And the answer there is no, right? No. So you can cancel factors, all right? So when people do this, and you got 3x squared minus x, and people say, I can cancel this x with that one and this with that one, is that okay? Well, yeah, it is actually okay, because actually x is a factor of the top, and x is a factor of the bottom, so then I can cancel, right? So as long as you remember you can cancel factors, you're okay. All right. Trig. We're going to have some more time to practice some trig, but it didn't say here, but let's assume it's in a fixed interval from 0 to 2 pi. So where does sine equal 1/2? We think of the unit circle, that would be here. And what other quadrant? Over here. Sine is positive in these two quadrants. 1/2, that would be pi over 6. Sine is the y value. So it would be here, so it'd be pi over 6, and it would be 5 pi over 6, which is 1 short of pi, 1 pi 6 short of pi, which is 6 pi 6. So the answer would be pi 6 and 5 pi 6. This will be on the next quiz. Being able to solve a trig equation without a calculator and being able to get these unit circle values. So I'm going to give you on that IXL website. Now, did you guys notice you got an email from IXL? We have a new login, and just follow those directions. It gives you the login, new login pages for Kearney Public. We have an account now with them as Kearney Public, and so it changed at your username, and I don't know if it changed your password or not. If you had already changed your password, I think it kept it, whatever, but it's got login instructions. Now I'm going to make that an optional thing. There's an IXL on solving trig equations. Some of you have done it already, but you can do it again. And then one of them is solving exponential equations. I think those are the two big ones we want to be able to do. Trig ones especially. So if you need some more practice on those, that is something you can do. Okay? All right, so we got that. Here we would factor out a sine. So we'd have sine x plus 1 equals 0. So either sine is 0 or sine is negative 1. So think of the unit circle. Where is sine 0? That'd be here and here, right? Or you could think of the sine graph, right? Where is sine 0? At 0, at pi, and back at 2 pi. So usually our interval is 0 to 2 pi, but it doesn't include the 2 pi. So we'd probably say, okay, x is 0 and pi would be a solution to that. When is sine negative 1? 3 pi over 2 on the unit circle, or down here, again, on the sine graph, it's negative 1 at 3 pi over 2. So x equals 3 pi over 2. So there's your solutions on that. Okay? So it's kind of a factoring and canceling kind of thing. Probably stick with sine and cosine on this next quiz for the most part. We're going to talk about tangents, so those other ones we'll probably stick with those. So knowing those trig things is going to be of value on the next thing. Okay? And then this one, I was just going to show you this one. This one you factor out e to the x. Oh, and something kind of interesting happens there. If I factor out e to the x, I get x squared minus 2 equals 0. When does e to the x equal 0? Right? Never. E to the x, think of the graph, it never crosses the x-axis. Do ln on both sides, you can't do natural log of 0, that's never. So it's just x squared equals 2, which would be x equals plus or minus root 2, right? X squared. So solving that. And then this one, we would actually get out our calculators and we would just do solve, put that in, comma, t, hit enter, it would solve. So that one you could actually use. Okay? All right. So that is kind of quick version of what was going on with the solving equations. Let's move along here into what we're going to do today. So get your notes out, and we're going to make or begin the process. You might want to start on a new sheet of paper here with this. Now, eventually, we get into chapter 3, and we'll really have a big list of these things. But actually, we'll have a lot of the list done by the time we get to chapter 3. But all right, we're going to start with using the writing down some rules that we've already kind of taken for granted. The first one, and we're going to use, when we do these rules, we're going to use our notation that I use for the power rule, the Leibniz notation. It's just going to be a nice way to write our rules. So I'm going to use this Leibniz notation, which all that means, I had several people ask me about this on the power rule. Do we have to find what d is, or was d mean? No, all this means is the derivative with respect to x. That's all this is saying. The derivative is, okay, the derivative of this with respect to x is. So we're going to start with this rule right here. that if I'm going to do the derivative of f of x, some function plus or minus some other function g of x, that we can simply, so all that is saying right there is that if I want to do the derivative of f plus or minus g with respect to x, the rule is that I can just do the derivative of f plus or minus the derivative of g. That's called the sum rule for derivative, which just means, and we talked about this, so if I have x squared plus 3x, to do that derivative, that's like two different functions. X squared is f and 3x is g. So if I have x squared plus 3x, I can do the derivative of x squared with the power rule, which is 2x. And I can do the derivative of 3x, which is 3, and I can add those together. That's all. Now, why is that important to write down? Because it doesn't work with multiplication. We actually did some examples of it. If I have a function times another function, like x squared times sine x, I can't just do each individual derivative and times them together. It doesn't work. Right? So now, so with that, you can see there's some value in that. Same thing with dividing. In chapter 3, we're going to learn a rule for multiplying and for dividing. The product rule and the quotient rule. Right? This is the sum rule. It's easy. You just do their individual derivatives. Okay, here's the next one. We talked about this one, but we never wrote it in a formal notation. If I have a constant multiplied outside of a function, so if I have 3 times sine x, what's the derivative of 3 times sine x?
Sine x.
3 cosine x. So what do we do with the 3? You keep it. It just hangs out there. Now what we talked about is it's a stretch. It's a vertical stretch, right? And so the slopes would all be 3 times as much. So that's why we keep it. So this just rule says if you have a constant outside of a function, then to do the derivative, you simply keep the constant out there and then do the derivative, whatever the function is that comes after. So if there's a number, a constant outside of a function, just let it hang out there and do the derivative. Okay, and then we also talked about this situation. What happens if you have a constant multiplied inside of a function? What do we say? So if you have sine 2x, what do we say? You leave it in and you kick it out. You have to multiply, because what happens, that squeezes the function, so all the slopes are now at new positions, so you have to leave it in the inside. And it makes them twice as much, so you have to multiply the slope by that amount as well. So we kick out the k, and then we do the derivative and leave the k in as well. So sine of 2x, the derivative would be 2 cosine of 2x. Right? The derivative of sine 2x would be 2 cosine of 2x. All right? So those are some rules we've already kind of talked about. We just haven't wrote them in that kind of format. All right, so let's keep going. Then we learned the power rule. Well, this isn't really the order we learned them, but this is the next probably important one. And this one says if you have x raised to a power, the derivative of that is n times x to the n minus 1. So that's the big one. That's the one we've used a lot up till now. And then we can combine that with all the ones we were talking about before, right? With if you have a number on the inside, you kick it out. And if you have a number, like if we're doing 3x cubed, we leave that 3 out in front. We bring down the 3. So we can combine these rules as well. All right, then we get into the ones that we have learned up till now, which is the derivative of e to the x is e to the x. It's its own derivative. So we talked about that a while back. Okay? Now, I was thinking about doing this, but I didn't know how long this other stuff would take, so I'm not going to do it. But I'm gonna just start us on it. So I told you the derivative of e to the x was e to the x, and we calculated some slopes, and we noticed the slope and the y value were the same, right? If you go on the e to the x graph, and what we're saying there is this. What was that? Oh. Okay. The derivative of e to the x is e to the x means that the slopes on the function are the same as the y values, which is really kind of cool. It's the only function where that happens. To really show that the derivative of e to the x is e to the x, so we really would have to go back to the definition. So I was going to do a longer drawn out version of this, but let me just do the quick version of this. So here's the definition of the derivative, right? So I would start this by doing, okay, what's f of x plus h? Well, you plug x plus h in, so I'd have what? Minus all over h. Now, what algebra could I do to this right here on top? Well, we did this the other day. Isn't e to the x plus h the same as this? Right? Because when you're multiplying, you add the powers. Right? And you're not going to have to do this, so don't worry about it. But that's what we could do algebraically on that one. I forgot my limit. Okay? Now, what can I do on top there? Now I can factor out an e to the x. This one works pretty slick. The sines and cosines ones don't work quite as nice. But I can factor out an e to the x, and that gives me e to the h minus 1 all over h. Now, as h gets closer and closer to 0, what's going to happen to e to the x? Well, now careful. As h gets smaller and smaller and smaller, what happens to e to the x? Nothing. Nothing happens to e to the x because it doesn't have an h in it. It doesn't have an h in it, right? E to the x will be unaffected by whatever h is doing, right? So nothing will happen. So as h is getting closer and closer to 0, e to the x will just continue to be e to the x, right? So really what this is e to the x. It's like I can pull it outside and I can just really focus on this part. What is that doing, right? Well, this we can type into our calculators. Remember how we were doing the calculator table thing? We can type that in our calculator, look at a calculator table, and notice that at h goes to 0, this part is going towards 1. And so we end up with e to the x times 1, which is just e to the x. So that proves formally that the derivative of e to the x is e to the x, because we actually use the definition of the derivative to show it. Okay, so I would say it's kind of cool just to see that it works, but we're not going to do that with every single function because they just get too messy to do. Okay, anyway, back to our rules. Now, we're going to start adding here now to some new ones that we haven't had yet. The question becomes, what happens if you have 2 to the x, or 3 to the x, or 4 to the x, some other exponential besides e to the x? So we'll use b as our base, and we'll just talk about b to the x. So this is just some random base rather than e. And it turns out it's very similar. The derivative of e to the x is just e to the x. The derivative of b to the x is b to the x. But then we have to tack on the natural log of b. Now again, remember when I asked earlier today, what's ln of 5? And you said what? Just some number. ln of 2 is just a number. ln of 3 is just a number. Okay? So what we're doing is we're saying there's just some number, some multiplier we have to tack on. Because what happens is 2 to the x is not quite as steep as e to the x, and 4 to the x is a little steeper than e to the x. And so what that means is that the y values aren't the slopes exactly, but they're, if you just take this multiplier times the y values, you'll get the slopes. And the multiplier happens to be this ln b. Now, it turns out that that would work on e to the x as well, right? We could think of this rule as e to the x times ln. But what's ln e? ln e is just 1, right? And so that's why it's kind of a special one. So there's another reason why e to the x, people say, why do you use e? Why don't we do 10 to the x? Why don't we do these other things? What's so special about e? Well, there's a special thing about e right there. It's the only one of the exponential functions where the y value is exactly the same as its slope. All the others differ by this multiplier. So, quickly, if I ask you for the derivative of 2 to the x, you would write 2 to the x times ln 2. 3 to the x would be 3 to the x times ln 3. So I always remember that by just thinking 2 to the x, 3 to the x. Oh, that's like e to the x, right? And the derivative of e to the x is itself. So the derivative of 2 to the x is itself times an ln 2. 3 to the x is 3 to the x times ln 3. And so forth and so on. Okay? All right. So that's your exponential rules. Moving on. we haven't, let's do the log because they're kind of related to the, we'll do the trig, save the trig for last. So let's do natural log of x. What's the derivative of natural log of x? This is an interesting one because most derivatives stay within the family. Have you noticed that? Derivative of sine is cosine. You do the derivative of trig, you get another trig. You do the derivative of an exponential, you get another exponential. You do the derivative of an algebra, like an x squared, you get another algebra, like x, 2x, or whatever, right? They kind of stay within the family. This is the only exception. The derivative of natural log of x is 1 over x. Interestingly enough. Okay? So here's the ln x graph. It comes up and goes like this. And so... Yeah, I was going to say, too bad we don't have a camera while we're recording this. It just, not. All right. So what happens is, as x gets bigger, but this kind of makes sense. What picture was it?
Log.
It's a log. Seriously? Wouldn't that be cool if it was the log picture right now?
Well, it might be. I know what you're talking about now.
That'd be kind of cool. All right. Anyway, the derivative is 1 over x. What that means is, as x gets bigger and bigger, what happens to the slopes on natural log? Smaller and smaller. Reciprocal. That's what happens, right? As x gets bigger and bigger, 1 over x gets smaller and smaller and smaller. Now, just because something gets bigger, as 1 gets bigger, the other gets smaller, doesn't mean it's 1 over x, but in this case, it actually is. It's exactly 1 over x. It's a reciprocal. So if I went out here at 6, the slope would be 1/6. And if I go out at 10, the slope is 1/10. And if I go out at 20, the slope is 1/20, all the way out. Okay? And that's what you get. And also, if you get in here really small, like 0.1, 1/10, the slope would be 10, right? And that looks like it'd be really steep, right? Makes sense. The slope would be like 10. All right, and you can't do 0. You can't. There's no value of 0. Of course, 1 divided by 0 would be undefined, which would be when it's basically vertical, but there is no point there anyway. All right, then, so what about other logs? So the question would be, if you got ln x, what about logs of other bases? Okay, and we're not going to run into those very often, so we don't have to worry about it, but it's kind of the same thing as e to the x. The derivative of e to the x is e to the x. Well, the derivative of 2 to the x is 2 to the x, but then you have to tack on this multiply. Well, the same thing is true here. So if we have logs of another base, the derivative is the same as it is with natural log. It's 1 over x, but we have to tack on this multiplier. And the multiplier is actually the reciprocal of what the multiplier was on e to the x. It's 1 over ln b. So if you're doing log base 2, right? If I'm doing log base 2, the b is this base right down here. B is the base.
Oh.
Yeah. So, what?
I thought it looked like a 10 triangle. It's just a poorly drawn 10. The B looks like a poorly drawn 10.
A well drawn B is a poorly drawn 10. Okay. All right. So you have a choice between a well drawn B or a poorly drawn 10. You're saying. So what you're saying is my handwriting. I get what you're saying. My handwriting's so bad that you go with the poorly drawn. I get you. All right. Anyway, so B is the base. So if it was log base 2, the derivative would be 1 over x times 1 over natural log of 2. That would be it's just this multiplier that you tack on whenever you do log of another base. And whenever you do an exponential with another base, you tack on just ln of whatever that base is. Okay, so that's the rule. We won't see those near as much. E and natural log we'll see most of the time. But that's what makes those a little tougher. These are the ones you probably have to study more because you don't see them as much. So you got to make sure you review. Okay? All right, let's go to the trig ones. All right, that's what we have left. We got 6 trig functions to put on there. One of them we know for sure. I think we talked about another one of them. But the derivative of sine is cosine. Again, don't worry about this notation. All this notation is a nice way for us to write our rules. All that is saying, when you read that sentence, is the derivative of sine is cosine. That's what that sentence is saying. The derivative of sine is cosine. And the derivative of cosine is negative sine. We did one of those where we looked at the slopes on the cosine graph and we saw it was making the sine graph but flipped, so it's negative sine. So we have to kind of remember those that way. Now where it comes into play, where that negative really sometimes gets confusing, is when we start doing this idea of antiderivative, going backwards. That's when these really get interesting. On your homework, there are some problems where they're going to have you do these derivatives, and they're also going to ask you about antiderivative on a couple of them. It's not going to be a big emphasis, and I haven't even decided. I'm not even sure I'm going to put it on the next quiz. And if I do, it'd be like one question. It's going to be a very small piece. Okay? But so I want you to try them on the homework. Just get thinking in reverse, because it does help you on your derivative rules. What you do is you said, really, to do an antiderivative, it's not really a rule. You just say, well, I think the derivative would be this, or antiderivative would be this. And to check it, you just do the derivative and see if it's giving you the right thing. So it's a good way to practice your derivative rules anyway. So I'm not going to make a big deal about it right now because I really want you to focus on the derivative rules, but expect a little of that in your homework. All right, derivative of tangent. We'll do an example up here so we can see it this way. The derivative of tangent is secant squared, and that's it. That's what it is. You got to memorize it, right? Derivative of tangent is secant squared. Now, don't ever forget, it's not going to be a huge deal for us right now, but it will become that secant squared is a lazy person's notation for that. Okay? It's not really going to be an issue for us right now, but it's, you've got to understand that's what that means. Okay? It really means a secant of x all squared. It means secant x times secant x is what it means. All right? But we write it that way. And we got 3 to go. So cotangent. There is kind of a connection here. You notice that the derivative of sine was cosine. The derivative of cosine was negative sine. We just did the derivative of tangent. It was secant squared. Does anybody want to venture a guess what cotangent is? Negative
Tangent.
Cosine.
Cosecant
Oh.
squared.
First try.
Cosecant squared. Right? So tangent, the derivative was secant squared. Cotangent, the derivative is negative cosecant squared. All right. And then that leaves us to go. Secant x would be the next one. The derivative of secant x is secant x times tangent x. Again, just one you have to memorize. The derivative of secant x is secant x times tangent x. Shift gears here a little bit. What if I wanted secant 2x and I wanted the derivative? You would kick out the 2 secant 2x tangent 2x, right? We said if there's something on the inside, it stays on the inside in your derivative. And then when you're multiplying something on the inside, we said you kicked it out too, right? We're gonna get a review that here in a second, but just wanted to throw that out. All right, last one is cosecant. And again, we saw that connection before, so if the derivative of secant is that, what do you guess for cosecant?
Negative secant.
Negative cosecant times cotangent x. See that? So the derivative of sine was cosine. The derivative of cosine was negative sine. The derivative of tangent was secant squared. The derivative of cotangent was negative cosecant squared. And then same kind of pattern there. So in a way, you've got 6 to memorize, but really if you memorize those 3, and then those other 3 that are related to it are just the negative other versions of it, it makes it a little easier to memorize. All right, there are our derivative rules. So I'll come back to that. Here's an example. Let's go through this little example right here. So write down, this is just going to be this is going to be a big part of what your homework is today. Okay, we'll do one here, and maybe we'll make up another one. We got time here. So here's a function, right? So first of all, our very first rule we wrote down said that if you're adding up or subtracting multiple functions, you can just do each one's individual derivative. So we're allowed to do the individual derivative of each one of these three terms here, right? Okay. Then it's just a matter of doing the rule, combining all those different rules we have. So f prime of x would equal the derivative of the first term, 3x squared, is 6x. That's our power. Along with the rule that says you just leave the 3 out in front, right? You bring the 2 down, drop it by 1, you got 6x. Now we're going to do sine 2x. Well, what do you do when there's a 2 in there? We kick out that 2 and leave it in. And derivative of sine is cosine, so this will stay a negative.
2x.
2 cosine 2x. So the 2x, the inside always stays the same. And that's why those parentheses around ln x and cosine x are so important, because you got to know what's inside the function. The inside always stays the same when you're doing a derivative and an antiderivative. The inside always stays the same. Okay? So the 2x is going to stay the same derivative. A lot of times you'll hear me say instead derivative of sine x is cosine x. A lot of times I'll say the derivative of sine is cosine. Because whatever's on the inside of sine is going to be on the inside of the cosine when we do the derivative. All right. And then what about this one? This is
3 to the 4x plus 1.
Yeah, you have to think of this as that rule right there. So, but the inside is going to stay the same, right? This is not a power. The one that always gets people is they always want to bring this power down. We don't do that when the x is up in the power. This is this rule right here. It's a number raised to an x, or some x's, which is what we have here. So we're going to have 3 raised to the 4x plus 1
Times
natural log 3. We're missing something. Times. What? What?
Oh, times.
What do we do with this 2 right here?
Times 4.
Times a 4. If you've got a 2 multiplied on the inside times your x, we had to kick it out, right? Well, we've got a 4. Now, we don't care about the plus 1. We said the shifts didn't matter on the slopes. The shifts don't change the slopes. They just change where they're at. So the fact that our plus 1 is still there in our derivative takes care of that. But you're multiplying here times a 4. Just like here, we were multiplying by a 2. We had to kick out a 2. Here we're multiplying by a 4. We got to kick out a 4. So we need a 4 there as well. Now, you guys that just came in, we were just working on a derivative problem. We went through our rules here. So, 3x squared, derivative 6x. Sine, the derivative is cosine, but we said you always leave the inside alone. And if you're multiplying by a number times the x on the inside, it gets kicked out because that compresses that graph, changes those slopes. Here, the rule for 3 to the x is 3 to the x. You always leave the inside alone. We said we got to kick out an ln 3. If your base is different than e, you got to kick out ln of the base, ln of 3, and we had to kick out a 4 because of that 4 in there. So again, all these rules get used in combination with each other. Now, do not worry about simplifying anything when you get done with these. Okay? Right now, we're focused just on the derivative rules, so we're not going to worry about having to necessarily simplify anything here. Okay? Now, what if I ask you, because this is what's going to happen in your homework, it's going to ask you for f double prime. Well, what's that mean? You do the derivative of f prime. So it's just we do it again. Oh, good. It's more practice. Woo! It's more practice for our rule. So what's the derivative of 6x? 6. What's the derivative of, again, here's this 2 out in front. What do we do with a number out in front?
We
Leave it there.
Just leave it there, right? So that 2 will just hang out there. What's the derivative of cosine? Oh, so that's going to turn that to a plus. Sine, what happens to the inside?
Keep it.
Keep it.
Kick it out.
But I got to kick out a 2, but there was already 2 out there, so there's got to be a 4 on there. So there's a 2 hanging out there. Derivative of cosine is negative sine, so it turns that into a positive. We kick out the 2, which is going to make a 4, and we leave the inside alone. All right, plus, now we got this doozy. However, it's not as bad as you think, because what's ln 3?
1 over 3.
No. Oh, I'm glad you said that. What's ln of 3? Remember earlier discussion? A number. ln 3 is just a number, right? ln 3 is a lot different than ln x, right? That's different. ln 3 is not ln x. ln x is a function. ln 3 is a number. Big difference. So what's ln 3? It's a number. What's 4? It's a number. What do we do when we have a number times a function? It just hangs out there, right? Remember what we were just saying that?
Yeah.
When you've got this 3 sitting here, we don't have any problem with that, do we? We got 3 sitting here, it just hangs out while we do the derivative. Well, this is a little more confusing, but it's the same thing. I got a number, I got another number, multiplied times this function, it's just going to hang out there. So I'll just save that to the end. I'm not going to do anything with those. They'll just tack on at the end. They're just hanging out. So what I need to do is this derivative. Well, what is that? Oh, it's the same one we just did, isn't it?
Yeah.
It'd be 3 to the 4x plus 1. We have to times by an ln 3
times 4.
because that's what the rule of this is. And the 4 I got to kick out. And I've still got these 2 hanging out there. So I guess you could square that and square that. You got to be careful on the square of that one. I'd probably put parentheses around it. ln 3 squared. Or you could just put another ln 3 and another 4 if you wanted to, or make it 16, whatever. But do you see why? Okay, again, it's putting these rules together. So this term right here goes together. Those 2 things are just a number that are multiplied. We said in our second rule we wrote down, when a number is multiplied by a function, it just hangs out there. So it just hung out. We did this derivative, which gave us another set of those times the ones that are just hanging out there. Okay. All right, now, really throw a wrench into this. We're not going to spend a lot of time on it, but what if we wanted to do the antiderivative? You just have to go in reverse. And all your thinking should be is this. What do I need to put there so that when I do the derivative rule, it'll give me the little f log? So, now this one we actually talked about. We know it's going to be x to the 3rd. What number has to go in front here?
You have to divide it.
What we said was raise it up and divide by that new power. So it'd be 3x to the 3rd divided by 3. Oh, it'd just be 1. Oh, sure, yeah. Oh, duh. X cubed, what's the derivative of x cubed? 3x squared, right? So whatever we put on this top line, when we do the derivative, has got to give us this. Oh, that's just x cubed. Okay, clear, easy enough. What about this? Sine. When we do the derivative, what do we need to get us a sine?
Negative cosine.
This must have been a cosine, right? The inside never changes, right? Inside always stays the same. Now, if I do the derivative of cosine, that is negative sine, right? So this has to be a positive, right? So the derivative of positive cosine would be negative sine. But the problem is when I do this derivative, I'll have to kick out a 2. There's no 2 there. So I better put a 1/2 there. And that is exactly how you think about it. You're just thinking in reverse. You're thinking, what do I need to put here so that when I do the derivative, it'll give me that? That is exactly your thinking on an antiderivative. It's a kind of a guess and check kind of thing. Derivative, we have rules. If it looks like this, we do this. If it looks like this, we do this. Antiderivative, more of a guess and check. This is the really crazy one. Definitely not going to have to do this on the next quiz. Don't even worry about it. But you know what? But think about it. A 3 to the x is its own derivative except for that multiplier out there, right? So look at every one of these derivatives. They all had 3 to the 4x plus 1, but when we do the derivative, we know we're going to have to tack on an ln3, and we're going to have to tack on a 4. But those aren't there. So there must have been a 1 over ln3, and there must have been a 1 over 4 there, so that when I tacked on the ln3 and the 4, they canceled out. Okay? All right. Don't worry too much about that antiderivative piece.
Where did the 1/2 come from?
The 1/2 came from, I know when I do this derivative of cosine, I'm going to get sine negative, and I know I'm going to kick out a 2. So when I do this derivative, I'm going to kick out a 2, but there's no 2 here.
Right. Okay.
So that if there's a 1/2 set in there, when I kick out the 2, it'll cancel the 1/2. Okay. All right, so that's just using those derivative rules. Now, Casey did make me think of one that is always tricky. What is the derivative of a number? What's the derivative of 7? 0. Derivative of 5? 0. So that's easy, right? Derivative of a number is 0. But what, and then, I don't want to put him on the spot, but everybody makes this mistake, or almost everybody makes this mistake. What's the derivative of ln3? Now, the first thing everybody thinks of is this rule we learned. Right here, right? Derivative of ln x is 1 over x. So when I ask what's the derivative of ln3, everybody wants to say 1/3. But ln3 is a number. What's the derivative of a number? 0. So the derivative of ln3 is 0. It's not 1/3. There's a difference between derivative of a function and derivative of a number. Okay? And so that's what you got to be careful of. What's the derivative of e to the 3rd power? 0. Because e to the 3rd power is a number. It's not e to the x. It's a number. Right? So you don't want to be, if I ask what's the derivative of 5 to the 3rd, you don't want to say, well, bring the 3 down in front. No. 5 to the 3rd is just a number. The derivative of a number is 0. So don't be fooled by that. Don't be fooled by that. All right. One last problem to do. One last problem to do here. This is number 35 on page 147. Number 35 on page 147. Okay? And you're going to have some homework problems that are similar. Okay? Now, this is a chart kind of a situation. So this is why we've learned these rules, so we can now apply it to what we learned last chapter with the chart. Where is a function increasing, decreasing? Where does it have local maximums? Where is all this stuff happening? The chart is really still the most important thing we've learned about derivatives. These interrelationships between functions is what's going to allow us to do meaningful problems using the derivative. Right? That's when did the ball get to its highest point? Well, when the slope was 0. When the velocity was 0, when it stopped. Well, we want to find that. We want to find when the derivative is 0. We're interested in those kinds of situations. So the chart is the thing. So how do we do that? Well, with these derivative rules. So here's our function. Now the questions on number 35 are this. Are there any stationary points between 0 and 2 pi? And they do include the 2 pi, so we will as well. Are there any stationary points of this function? Where is this function increasing? What are the max and min values? Where is f concave down? Where is f increasing most rapidly, right? Those are all chart kind of questions. So where do we start? What's the first column in the chart? Stationary point, which is the first question they ask. And where are stationary points? When f prime is 0. It's the most important thing we care about. I said this earlier. Most of the time this year, you're stuck on a problem, you don't know what to do. Do the derivative, set it equal to 0. Right? So that's what we're going to do. F prime of x. Turns out that's what we want to do here, because the first question is, are there any stationary points of f? Well, that's when f prime is equal to 0. So what's the derivative of this? Well, what's the derivative of x? 1. Right? X would be like the line y equals x, the slope is 1, right? Or power rule, bring the 1 down in front, drop that to a 0, right? You start to learn that anytime you have x to the first power, whatever the number is in front, that's what the derivative is. So it's 1. Derivative of cosine? negative sign, so that's going to turn into plus sine x equals 0. We want to do the derivative, and we want to set it equal to 0. Okay? And we want to solve that. So what do? So now you can see why we did that worksheet, right? So now we're solving these equations. So where does sine equal 0? On the unit circle, it would be the y value -1, which is down there. On the sine graph, it would be where does sine equal -1, which would be down here, which is at 3 pi over 2. Okay? So when x is 3 pi over 2. Now sometimes we get more answers than that, but it will get multiple answers, but this time that's all we get. Now think back to the last quiz, think back to the problems we were doing. Now it asks, are there any stationary points? That was part A. Yes. If so, where? We just answered it. X equals 3 pi halves. Next question. Where is f increasing? Number line. We want to do a number line. Often, after we do f prime equals 0, the next step is number line. Okay? Because that gives us chart information in our number line. So we're going to put our stationary point on our number line, and we're going to pick some points on either side. Now, I would not pick numbers like 1 or 2, because we're going to be plugging those into our f prime. So we're going to be plugging them into sine. So we want to pick numbers we know their value. So what's less than 3 pi halves? Pi fourths, pi halves, pi sixths. Pi would be a good one. This is probably best, pi, okay? 3 pi halves, what would be good out past that? 2 pi, right? Those would be easy ones to plug in. So we're going to plug pi into the red box here. Sine of pi is right there. That's 0. Plus 1, that's positive. Sine of 2 pi, which is right there, or right there, also 0. 1 plus 0, positive. Oh, so what do we got? We must have a flat spot there. Okay? So where is this function increasing? Always, right? Always increasing. Find the max and min values. Now, we're going to talk tomorrow more about global max and min, because we haven't talked much about that. We're going to talk about local max and min. We don't have any local max and mins here, do we? All we got is a flat spot, right? But it says, where would there be max and min values on the interval 0 to pi? Well, what did we just say this number line told us? F always increasing. So where's its lowest point have to be? At the left edge, which is 0. X equals 0. And its biggest value at pi. They said from 0 to pi in this problem, right? From 0 to pi. So at pi. Now, but it did say, find the max and min values of f. So what does that mean they're asking for? The inputs or the outputs? They want the outputs. When they say where is the max and min, they want the input at x. But if it says find the max and min value of f, it means the output. So you would have to plug a 0 into where? The original. So 0 minus cosine 0, what's cosine 0? 1. So 0 minus 1 would be -1. That'd be your min value. And then the max would be plug in a pi. Pi would that'd just be pi, 3.14, right? And what's cosine of pi? Cosine of pi is -1. So pi minus a -1. So that'd be pi plus 1. That's your max. I just leave it pi plus 1, right? Don't even mess with decimal. We'll worry about pi plus 1. So your biggest value would be that. Okay? Because we know the function's always increasing. Now we're going to get more into global max and min tomorrow, but that's what that's saying. Where is f concave down? Okay, but that's hard to judge. We don't have a way of saying when something's decreasing. How do we tell when f prime's decreasing? When f double prime is negative. Remember I said at the beginning of the period, if you're talking about concavity, f double prime's involved, right? F double prime's involved. So f prime's decreasing is when f double prime is negative. Well, let's do a number line, except not an f prime number line. Let's do an f double prime number line, right? So everything we just got done doing, we would repeat with f double prime. So f double prime of x would be just this derivative. So derivative of 1, 0. Derivative of sine, cosine. Where does cosine of x equal 0?
I halves and 3 halves.
Cosine is the x value on the unit circle, right?
Yeah.
So cosine, so basically you're saying where is x 0 on the unit circle would be a pi halves and it'd be a 3 pi halves. Okay? So pi halves and 3 pi halves. Those are possible inflection points, right? Which means those are possible changes of concavity. What we want to do is do a number line. Because we're interested in what again? When f double prime is negative is what we care about right now, right? So to find it, we need a number line. Well, first we need to know where is it 0. So we do our number line. F double prime, we put in pi halves. We put on 3 pi halves. What are some numbers in between? Pi be in between.
0 and
2 pi to be over here, 0 to be over here. So we plug those in. 0, cosine of 0.
1.
Cosine of 0 would be over here, it'd be 1, right? That's positive. Cosine of pi, negative 1. Cosine of 2 pi, back around here to 1. So what does that tell us? Now that's f double prime, remember? So let's think about this. This number line tells us, if this is f double prime, that tells us what about f? Concave up, concave down, concave up. So we do have a couple of inflection points there, don't we? We have some changes of concavity. This told us flat spots, local max and mins, f prime. This f double prime told us concavity. Now that'd be local max and local min of f prime, right? Which of course is where inflection points happen. So all that stuff from chapter 1 comes back to us here. Now, the question was, where's it concave down? Between pi halves and 3 pi halves, right? See what's going on? So we're doing the same sort of thing that I was asking you last quiz, but we were doing just algebra type equations when we were solving, right? And doing these number lines. Now we're adding in the trig equations, exponential or log equations, right? And asking these same questions. So it's a matter of solving those type equations. But the number lines, and then we've added in the second derivative too. But it's really the same thing. It's doing the number lines. It just gives you different information. F prime tells you when F's increasing and decreasing, so it tells you local maxes and mins. F double prime tells you when F is concave up and concave down, so it tells you inflection points. Okay? So, but working it is really the same process. Now, I will say that there'll be a lot more of this with the trig than there will be the e to the x. Because think about e to the x graphs. Very much interesting chart stuff. Always increasing, always concave up, no local maxes or mins, no flat spots, no inflection points. I mean, there's just not much going on. So in the e to the x section, the log section, you're not really going to get much chart kind of question. But sines and cosines, there's a lot going on. All kinds of local maxes and mins, inflection points, changes of concavity, that kind of stuff. So we would expect to be sticking mostly with these. Okay? The e to the x will be some solving and some stuff, but that's what's going on there. Okay, here's your homework for tomorrow. And there's really only this problem right here, 10 through 13, that's your chart. Welcome back. This is your chart stuff right here, you know, so where you're doing the derivative, setting it equal to 0, maybe the second derivative, setting that equal to 0. That's that 10 through 13 section. These are really, and this section is exponential and log section. This section is the trig section, okay, 2.7. So that's why we're doing two different sections. Basically what they did is they had one section talk about exponential log functions, and they had one section talk about the trig functions. So we really talked about two different sections at once here. These sections here are just derivative rules, these little pieces here. Now you can check those on your calculator if you want, you know, as you're doing them, but you know, we'll go over them tomorrow. So these sections, these bigger sections here, talk about the derivative rules. Actually, I think 6 and 8 are too. I think 6 and 8 say something like, use theorem 12. Well, if you look back at theorem 12, it's just the derivative rules for log and for e to the x. I mean, so you're not really using theorem 12, you're just Just do the derivative. I think it has you do the derivative and plug some numbers in. Is basically what it said. E means even, yes.
Can we switch that to odd? Yes.
Yeah. Yeah, do the odd. Seriously, I mean, do the even, do the odd, do them all. Whatever. Yeah, no, you're right. When I come around, I would say, because you want to say you just want to look at the back of your book real quick. Absolutely, I don't care. That's fine.
So we good?
Good. After when I come around and you did the odds instead of the evens, I'm fine. Okay.
Sweet.
Yeah, I'll be honest. I don't know why I did evens. I don't care if you look at the back. You know.
You're switching to
So
the option. So it's an option.
It's an option. I don't care. Yeah.
I thought he was joking.
No, I'm serious. I am serious. I mean, but now listen. On your calculator, on your calculator, okay? Because when I come around and do the points, and if all you did was just write down on the back, I mean, whatever. If those 2 points are that important to you, then I guess go for it. But it's going to cost you a lot more than that on the quiz if you don't know how to do it. So that's fine. But here's what you can do on your calculator, right? You can come onto your calculator here. I think I showed you this. Next to the 9. Remember this thing right here?
Yeah.
The derivative rule. So you hit that. Whoops, just get to the scratch pad. Go here, do the derivative, put an x or whatever my variable is, and if my problem is x raised to the third, right arrow plus, let's do a new one we just learned here. E raised to the, what do we do? 4x plus 1. Oh wait, no, let's don't do e. Let's do it. What do we do? 3 raised to the 4x plus 1. So if that's one of your problems and you want to check to see if you're doing it right, your calculator will do that for you, right? So let's look at it here. Now, it writes it in a little different order than I would have. I would have done x cubed, derivatives 3x squared, so I would have had that first. And then we said it's 3 to the 4x plus 1, right? So when we wrote ours, we did this. We said it was 3 to the 4x plus 1 times, what do we say, ln 3 times a 4 kicked out. Now notice theirs is a little different. They got 81 raised to the x. Well, what they did here is they did some algebra. Now you're going to say, well, that would be confusing. Well, not really. Here's what I would do if I was you. I would take your answer and I would type it in and to see if it gives you the same as that. But let me show you algebraically, since we don't have a whole lot of time left for you anyway. What they did, what the calculator was doing, and I'm not going to make you do this, what the calculator did is they simplified this piece right here. 3 to the 4x plus 1 is the same as 3 to the 4x times 3 to the first. Would you agree with that? Because of the adding the powers thing. And 3 to the 4x is the same as 3 to the 4th to the x. Because when you have a power on a power, what can you do? Multiply the powers. So 3 to the 4 raised to the x is 3 to the 4x. Now what's 3 to the 4th? 81. So this is 81 to the x, and this is a 3, which they combine with your 4 to make it 12. So you got your 12, you got your ln 3, you got your 81 to the x plus your 3x squared. So when you're using your calculator, right? So here's what I would do if I looked at their answer and said, oh gosh, that's not what I got. What I would do is type in, because remember, your calculator is going to simplify things that you put in. So if I'm going to type in what my answer was, which was 3 raised to the 4x plus 1, and what else did I have? Times ln 3 times 4. Here's what I had. I type that in, I hit enter, and it simplifies it, and I go, oh, yeah, okay. My answer is the same as what they get. See what I mean? So that's how you can check. So even if you do the evens, right, you can get your calculator out and you can check it as well. Okay? So either way, if you want to do the odds, so you can look in the back and look at those, that's fine. Because I'm not sure how they write them in the back. I don't know if they'll simplify them some. So you have that same issue when you look in the back of the book sometimes. You look in the back and you say, that's not what I had. Well, they may have simplified it in some weird way that you're not maybe required to do. Okay? So you always do have to consider that anyway. All right. So, anyway, That's Board of Alderman.